Let us consider Dirac brackets. Bra-kets. So this is a notation invented by Dirac, and it's pretty neat for quantum mechanics. It's used by many people. For some problems, it's absolutely very convenient, but it's just another way of writing the same identities and math that we've been doing so far. So in order to understand Dirac brackets and to be able to use them, because they're actually quite convenient in some cases, there's basically two steps we have to take. The first step consists in learning how to go from inner products to brackets. So one step is inner products to brackets. And the second step is the one in which you go from brackets to bras and kets. From brackets to, let me say it, kets and bras. So that's a step when you isolate these two kinds of objects that are called kets and bras from the brackets you've introduced. So the first step, as we were saying, it's not very complicated. In fact, it's almost a triviality. It's just a change of notation. Well, we denoted an inner product, UV, in this way, and now we're going to change notation, and we're just going to say this is equal to U, and instead of the comma, we put a vertical bar and V. So you can take this as the definition of this thing on the right is equal to this thing on the left, and that's a bracket. In the two, the bra and the ket put together, as we will see. Now recall, if you have U and V, this object belongs to the vector space, this object belongs to the vector space, this label inside the left side belongs to the vector space, and that other label belongs to the vector space. So the bracket is this composite object in which the comma has been replaced to a vertical bar. And then you have to wonder how things look. And, we haven't done almost anything, but things look a little different. And let's just go through some examples to see that we can understand how things look or what they mean in the new notation. So examples. Example 1. That's one example. All right, so take U, inner product with this, that was supposed to be a comma, C1 V1 plus C2 V2. Well, that is equal to C1 U V1 plus C2 U V2. Well, if we translate it to brackets, you would write U vertical line C1 V1 plus C2 V2 is equal to C1 vertical line U V1 plus C2 U V2. So that's how it looks. Not very different. It's probably important to do an example where you have things on the left side of the bracket. So example. You remember this property of conjugate homogeneity. So if you have C1 U1 plus C2 U2 with V, that was equal to C1 star U1 V plus C2 star U2 V, comma, I'm already drawing brackets, V. So in bracket notation, you would write C1 U1 plus C2 U2, V equals C1 star U1 plus C2 star U2 V. Remember, that was supposed to be just a comma. Anyway, doesn't look good. So this is how the property that you're familiar with looks with brass and cats. There's other things you could imagine. The definition, for example, of the norm of a vector squared used to be V inner product with V. Now you would write V. Or Schwarz's inequality. It used to be UV inner product norm is less than or equal to UV. Now it just reads UV less than or equal UV. So it's all quite straightforward, and there's nothing much except just getting accustomed to look at inner products and to see that they look a little bit different now. Another example that will be useful later: if you have an orthonormal basis, ON basis, we would say, okay, EI directly with bracket notation, EJ, that was supposed to be the inner product. You remember, this is delta IJ. In this case, if you have an arbitrary vector and you want to write it as a superposition of the basis vectors, then remember, you figured out what alpha I was by inner product of a basis vector with V. So alpha I, if you do this time, it would be EI inner product with V, that you write it like this already. So the formula for V now looks like, in bracket notation, like alpha I EI. Let me write the EI first, and then EI V. So that's another way of writing the decomposition of a vector in terms of basis vectors. And so far so good. We've basically just done the first step of translating from inner products to brackets. Now we do the second part, which is a little bit more interesting. We're going to try to go from brackets to cats and brass. So this is step 2. And the idea is that you have this bracket now, which is the inner product, and from this you want to invent two quantities that have a separate existence. It's as if you have these two objects here, and now you're going to spread them apart. The only thing that existed before was this composite object, but now you want to stretch it out in such a way. So we want to stretch it out in such a way that you have the object U and you separate it from the object V, and you have two objects, two kinds of objects, object that is called a ket and an object that is called a bra. Now, let's begin with cats. They're a little bit more familiar. So the cats represent a funny notation. The cats are really vectors. Remember, you have a vector V in the vector space. Then we'll say that V is also in the vector space. The whole decoration that we're putting around the V to make it a cat doesn't change the meaning of the object. This object is the same object as this one. both belong to the vector space. So you would say, why do you put the ket? Well, you put the ket a little like the arrow that you put sometimes on top of a vector to denote that it's a vector. It kind of tells you that this is a vector because sometimes it may be not so obvious. In fact, the basic idea of this notation is that you put the vector inside this object, but sometimes we play with the label of these vectors, and it's important to realize that the label, so you have a label inside this object, runs into two possibilities. Possibility I and possibility double I. In the first possibility, the label is a vector. Well, is a vector. In the second possibility, the label is a property associated with a vector of the vector. It's not a vector, but rather some thing you can associate to a particular vector. For example, so in case I, what do we have? Suppose you have an operator T that is a linear operator. Well, in this case, T acts on vectors. This is what we call the action of the operator T on the vector V. Now, how would we call it? Well, we would say it's the operator T acting on the vector V, but that's the same as the ket V. Now, by definition, this is the vector TV. So you could also say that this is, by definition, also TV. So this is funny about the notation with kets. You can bring the operator in if the label is a vector, because you understand here T is acting on the ket vector V. And it gives you the ket or the vector TV. And there's nothing inconsistent about this notation. On the other hand, let's consider case 2. Good example of this case is, you remember our spin states, we call them plus, minus, we even call them n vector plus, and these labels have nothing to do with vectors. Plus or minus are signs, and n is a unit vector. It's nothing to do with the state you're representing in the vector space. Nevertheless, these things are states in the vector space. When you have such thing, you cannot use this notation. If you have Sx, for example, acting on the state plus, you would not write it as Sx plus, because Sx acting on plus, what does it mean? So you don't use that. So you don't bring the operators in when your labels are properties of the vectors, and that's familiar. So this is it for kets. We've said they're just vectors, and we can therefore proceed now to the brass. So the question is, what are brass? Well, to understand brass, you have to remember this concept of linear functionals we introduced before. What was a linear functional? Phi, a linear functional phi was an object that acted on vectors and gave you numbers. You could write f. Of course, today f is going to be the complex number, so that is not so important. So basically, phi takes a vector v and gives you phi of v, which is the action of phi on the vector v. Now, we proved that for every phi, there is a unique vector in the vector space. For any phi exists a unique u belonging to the vector space such that phi acting on the vector can be reproduced by u acting on the vector through the inner product. And we even call this, guys, phi sub u, because the phi is kind of built with u. So phi u of v is equal to u v. So these were our linear functionals. Now, the interesting thing about linear functionals is that they form a vector space themselves. So it's funny how you have vectors, vector spaces, and then suddenly objects that act on this vector space, like operators, form a vector space, and linear functionals that take vectors to numbers also form a vector space because they can be added and they can be multiplied by constants. So a linear functionals, the linear functionals form a vector space V star. So the space V star is the space of linear functionals. And these linear functionals can be added. And it's kind of trivial if you have a linear functional phi 1 and a linear functional phi 2. You can add them, and the definition is that this added linear functional acting on V is nothing else but phi 1 on V plus phi 2 on V. Similarly, if you have a linear functional, you can multiply it by a number and define this thing to be a new linear functional that acts on the vector V by taking A times phi of V. Since all these linear functions are represented by vectors, there are as many vectors, as many linear functionals as there are vectors. So this V star is very closely related to V. And in fact, since it's parameterized by vectors, we have the dimension of V star is equal to the dimension of V. That's why V star is called the space dual to V. All right, so now comes the big idea in some sense. So let's think of how these objects act. So phi u acts on a vector V by giving you uv. And now let's think of a bra. This is a bra. Just like the linear functionals are labeled by a vector, the bra is labeled by a vector. Just like the linear function can act on a vector, the bra also can act on a vector in a very simple way. It just does this, and it gives you a number. And this number is the same as this number because this is just a matter of notation. So what you learn from here is that we can simply identify or set these two things equal. Phi u is the same thing as u. So that's what bra really is. Is the linear functional. And if you keep that in mind, you never get in trouble.